Okay, so we're going to continue on here, like I said, for a little bit, get a little bit deeper into here. So we started talking about a galvanic cell, and again, you do need to obviously know the basic setup of a galvanic cell, like you would produce there in a laboratory. As we just talked about there at the end, a cell diagram is sometimes used as sort of a shorthand to represent the galvanic cell. And again, it's always anode to cathode, the way those guys are set up. And as I mentioned, sometimes there will be some other stuff sort of inserted in there, especially, for example, like this one here, where there's a sort of a gas being used as an electrode. And obviously we use something like, for example, in this here, platinum as sort of the physical part of the electrode. So we got something to kind of connect the wire to. So when we're dealing with galvanic cells, we oftentimes will deal with what are referred to as standard reduction potentials. And standard reduction potentials, as we will see, is sometimes abbreviated as SRPs, or standard reduction potentials. So if we hook up this galvanic cell here, for example, where zinc is our anode over here, and our hydrogen is actually our cathode in this particular case. So once again, here it is the zinc that's going to go for a swim there into zinc 2 plus, giving up the electrons, which are going to transfer to the other side. This is some hydrochloric acid, which means you've got a good H plus supply in there. So as the electrons come in, it is going to reduce the H plus into hydrogen gas, which is why we see bubbles, I'm assuming, in here as well. And in this case, like I mentioned, the cathode here is actually our hydrogen. And obviously there is no kind of physical version that you could kind of hook up. So here they are using a platinum electrode as the physical electrode. When we look at our cell diagram, once again, this is our anode compartment here. That is our salt bridge. And then we have our cathode reaction. And again, on the cathode side, we do have a little bit more information. Since hydrogen obviously is a gas, sometimes people will insert obviously the pressure there. That is standard pressure, just like the concentration here is standard concentration value of 1 molar. And then we have one extra thing sort of inserted, which again is sort of the physical electrode that's being used in this particular case. The sort of reactant product still works and still comes out the same when we look at the overall reaction. This is our reactant and this is our product. So reactant and product. And this on the other side of the salt bridge would be our reactant and our product. And once again, we see our reactant and our product here. Overall, what's happening here is, again, the zinc is losing the 2 electrons, becoming oxidized. The H plus is picking up those 2 electrons and becoming reduced. Obviously, we could hook this up and get the cell voltage that occurs in this particular case. Nice super zoom. There we go. So our standard reduction potential is the voltage that's associated with obviously a reduction reaction. So we're going to see an SRP table, and an SRP table is basically a standard reduction table, which means every single reaction in that table is written as a reduction reaction. That's a little problematic in certain cases, as we will talk about, because if you have a reduction, you also have a oxidation that's occurring. So we're going to talk about 2 ways to take care of what you find in the table. And it may not make sense until we start doing problems. But much like in chemistry, when we have a hard time maybe directly measuring certain things, we oftentimes like to sort of place something as a standard to use to compare everybody else to. So for the standard reduction potentials, it is the hydrogen electrode, which is sometimes referred to as the She for standard hydrogen electrode, that they just sort of arbitrarily use as the standard to compare everybody to. They assigned it a value of 0 volts. So the reduction potential for hydrogen, and again, we see this is a reduction reaction. Electrons on the reactant side has a standard reduction potential of 0. So basically what they did is take this hydrogen electrode and basically just kind of hooked it up with a voltage meter with different metals, and we're able to do a calculation to figure out basically the standard reduction potential of a whole list, obviously, of substances. So if we take this like the one we just were looking at, which is the zinc and our hydrogen gas, and again assigning the value for the hydrogen electrode as 0, we could calculate the standard reduction potential of zinc in this case. So when they put this cell together, they get a cell voltage of 0.76 volts. Now, this is an important equation, and this is the equation I was just talking about, and perhaps this will not make any sense at this moment, but maybe it will. So you can calculate the cell voltage or the cell potential by taking the E of the cathode minus the E of the anode in this case. So it's cathode minus anode, and you would get these values from a table. So in this particular case, our hydrogen is the cathode, and our anode is the zinc, which means the cell voltage was 0.76, and our E of our cathode, which was our hydrogen, was 0, basically. So I should probably just write 0. Minus the E of our zinc. And in this particular case, rearranging, bringing the zinc to the other side, then 76 to the back side, does give us a standard reduction potential for zinc of minus 0.76 volts. Now, this equation can be used to calculate the cell potential or the cell voltage. If you use this equation, you should not change the sign that you see in the actual SRP table. So what I mean by that is when we look at the table, you will have something like a E plus, something gives you X. And it will say E naught is equal to 1.00 volts. And then you'll have maybe an E plus a Y here. That will give you a Y. And they'll say maybe this guy is negative 0.5 volts, right? Now, if we had a reaction where we had, let's just do X plus Y goes to X plus, do Y plus here. So we'll do something like this. Now, when we look at this, this is X plus going to 0. So that is plus 1 going to 0. We'll see how I did here. Is that being oxidized or reduced? That is being reduced. And we have Y going from 0 to plus 1. That is being oxidized, right? So if we wanted to calculate E of the cell, we would go, our E of the cell in this case would be our cathode, which obviously would be my X in this case, minus my anode, which would be my Y in this case, which would be minus 0.5 volts. And that would give me a 1.5 volts for my example. Technically speaking, when you have a E value that's written for an equation, it is supposed to be written exactly how that equation is. But the value that we're using here is actually a reduction reaction. We actually want the oxidation reaction, right, for Y. So if we wanted the oxidation reaction, we would flip it around, and it would actually be Y would go to Y plus an electron, and that would be the oxidation reaction for it. And when we do flip it, what happens to the E is actually the sign changes, and it would technically be plus 0.5 volts if I flip that guy around. So the subtract that is here actually changes the sign for you, and you should not change the sign, even though technically this is the correct value for the reaction that we're using. If you want to subtract, you should leave the value like you find it in the table because the negative actually changes the sign for you. If you want to change the sign, you should actually add both values together after you change the sign. So if I change the sign, I would take 1 plus 0.5, which would give me my 1.5 in my example here. If I want to subtract, I would leave it just like I find it in the table and subtract it because that's what the subtraction is for. It actually does the changing of the sign for you. I would recommend pick one way and stick with it, yeah, and not like flip back and forth because you'll change the sign and not subtract or do something weird like that. So again, it may not make a lot of sense. We'll do some examples in just a second here that will maybe help make it a little bit more sense. But take home message is if you want to use this equation like it's written when you go to that table, even though technically the sign should change for the oxidation one, don't change it because that's what the subtraction's for. If you want to change and be perfect like it should be, you could change the sign, but you should add them together after you change the sign for the oxidation one. Otherwise, again, you'll be off in terms of the sign. But again, we could use this equation like we saw here to get our value for zinc. We could then hook up, for example, the standard hydrogen electrode as our anode in this case. And if we did that and hooked it up with copper, what we actually see is that we get a cell voltage of 0.34. But in this particular case, the hydrogens actually are anode. And the copper here is our cathode in this particular case. It also demonstrates a couple of things. Pretty much anything could be an anode or cathode, depending on the situation. Just depending if you put them together right, it will work. If you put the wrong things in the wrong spot, it will not work. But the beauty of a galvanic cell is if it doesn't work voltage-wise, you just switch them. Make your anode your cathode and your cathode your anode, and then it will work, and it'll give you a positive voltage. So again, kind of going through our reaction here. Here is our hydrogen going from 0 to +1 being oxidized. Our copper going from +2 to 0 being reduced, and our overall reaction that is occurring here. So the standard reduction potential, here's a table similar to one I think you got in your book. And again, if you look through this table, every single one of these reactions are a reduction reaction. And as I mentioned before, technically speaking, if we wanted the oxidation reaction, we would need to reverse what we see on this list. So for example, I'm going to attempt to try to see this one here. Well, it looks big enough, maybe. So if we look at this reaction right here, again, we have the Cl2 plus the 2 electrons make 2 Cl minus, which has a standard reduction potential of 1.36 volts. If I needed this guy as the oxidation or the anode, I would flip the equation around and it would be 2 Cl minus goes to Cl2 plus 2 electrons. What would happen for my standard reduction potential is the sign would change to 1.36 volts. That's negative, sometimes referred to as a standard oxidation potential as well, because it's really an oxidation reaction here. So if I chose to do that, I would want to use that equation and add the numbers because I already changed the sign. I would not want to subtract it because then it would just put the sign back to where it was originally and you would get the wrong answer. The reason I point this out is if you are asked to give the potential for a reaction like this, the correct answer actually is with the negative value because it is written as an oxidation reaction. Just like the correct answer for this guy, if you wanted the standard reduction potential, should be the positive version of it because it is a reduction potential. So technically speaking, when you write in half reaction, be it a reduction reaction or oxidation reaction, the E value that goes with it should technically be the appropriate one with the appropriate sign. But oftentimes we just kind of go to the standard reduction table and just leave the sign alone and use the subtraction. So it just does the changing for you. But again, if you had a more specific question where it says give the E value for this specific reaction written as an oxidation, it should actually be the negative 1.36 would be the correct sort of voltage for it. Question on that. Here's another table. Here's another table which clearly you can read. But let's talk about some of the things that we see in this table. As I mentioned before, when you do sort of quote an E value, as I was just mentioning, it should be really for how the reaction is written. Now, how do you know when you put two things together, what's your anode and what's your cathode? You could actually use the SRP values to help you decide which one should be the anode and which one should be the cathode. The more positive E value that you find on the table has a greater tendency to be reduced, which means it should be which one, the anode or the cathode? Should be the cathode, yeah. So if you're given a problem where it just frankly says you built this galvanic cell with these two things, and that's pretty much all it told you, you would go to the SRP value table. The one that is more positive should be your cathode, and the one that is more negative should obviously be your anode in that particular case. With that being said, if they actually tell you how the reaction is happening, you do need to follow with what they tell you. So if they give you an equation, you need to actually look at the equation and go, that guy's being oxidized, so that's my anode. This guy is being reduced, that's my cathode, which may not agree with your table. But if you're not given any information about the reaction or how it's happening, you strictly could go straight by whichever one's more positive should be your cathode. Whichever one is obviously less positive there would be your anode. Half reactions are reversible, as I just did on the previous slide there. If you flip a reaction around, which technically speaking, if you needed to write a balanced equation, you would need to take one from this table for the anode part and flip it around. You technically should reverse the sign of the E that you find in there. Now, if you need to multiply one of these SRP reactions by a coefficient, which means if you're asked to write a balanced equation, you need to take one and flip it. Same rules apply with a redox reaction. We need same electrons in each. So you may have to multiply one half reaction by a number or two like we did in the previous problems. Unlike most things, you can multiply that reaction by as many numbers as you want. The E value does not change. So it's unaffected by if you need to multiply. So unlike delta H or something like that, where you multiply by 2, then you multiply the delta H by 2, you don't do that with E. So if you need to multiply to get the right number of electrons, you can do that. The E value for each of those half reactions will still remain the same. Any questions on that there? All right, so let's try one, shall we? Calculate cell voltage here of a galvanic cell that's built out of cadmium and chromium. These are some SRP values that you would find in the table. While you're at it, why don't you also write the balanced overall reaction as well. So first off, we want to calculate cell voltage. We can use our E of our cell is, again, our cathode minus our anode. And again, if you want to subtract, you obviously should leave the signs the way it is. If you want to add, obviously you need to change the sign. Which one here should be our cathode? It should be this guy, right? It is more positive, I believe. So that should be our cathode. That should be our anode. So to calculate E of the cell, we could just go right in there because we are not going to change the sign because we're subtracting in this case. This would give us our minus 0.4 minus our minus 0.74 volts. And I believe that's a 0.34 volts, if I am not mistaken. In this particular case, that would be our cell voltage. Question on that one. Now, I also asked you to balance the equation. So technically speaking, just to show you the alternative way of getting there. In this case, because the first one is our cathode, it is written correctly, right? So it is written as a reduction reaction, which means the E there is going to be minus 0.4 volts. The second one actually needs to be reversed, which is the chromium. That would go to our chromium 3 plus our 3 electrons, which means technically speaking, since I reversed it, I should now make that a positive 0.74. And I can't add these together yet because I don't have the same number of electrons, right? Which means I need to multiply the top guy by 3, bottom guy by 2 to do that. And if I do that, I will get 3Cd2 plus 6 electrons gives me 3Cd By multiplying by 3, does it affect my E value? It does not, actually. It stays the same. So that would be minus 0.4. Multiplying this guy by, I guess I do have my electrons there. We should have our 2Cr goes to our 2Cr3 plus our 6 electrons. Once again here, not going to affect my E value, which means if I add these together, we should have our electrons that cancel, giving us really our balanced overall reaction, which is 3 of these cadmiums plus 2 of the chromiums go to 3 cadmiums with no charge plus 2 of our chromiums with a plus 3 charge. By the way, this is also should be balanced both ways, elements and charge. Overall charge on the left is plus 6, overall charge on the right is plus 6, and 2 chromiums on each, 3 cadmiums. Now, alternative to what we did up here, because we changed the sign, I would not want to subtract in this case. I would want to add both of these numbers to find my E of the cell, because I chose to change the sign, which is perfectly fine to do. And obviously it gives you the same answer. So this is what I was talking about. If you choose to change the sign, which by the way, this number here is the correct one that goes with this reaction the way it's written. If you do change the sign, make sure you add. And again, if you don't want to bother with changing the sign, just subtract what you find in the table. Any questions on either way there? All right, so let's try another one, I think, that you got there. In case you missed that one, it's just super. All right, a galvanic cell is made up of magnesium and a silver electrode. Again, these are SRP values on there. Let's calculate the cell voltage for this one here. See what you come up with. All right, so in this case, we didn't really ask to balance any equations. So we really could just go based off of our SRP values that we got from a table. We could clearly see here that the silver is more positive. So that should be our cathode. And this guy should be my anode. So again, if we were to have to balance this equation overall, we would want to flip the magnesium. We also would need to multiply the silver by 2 and then add them together. In this particular case, I'm just going to subtract. So I'm going to use the E of the cell is our E of our cathode minus our E of our anode. And again, that's going to flip the sign for me, so I don't have to worry about it. So my cathode being 0.8 volts minus my negative 2.37 volts yields me a 3.17 volts, which is a positive voltage, which is actually a good thing. Positive voltage is good, spontaneous. Negative voltage, not so good, not so spontaneous there. Again, sort of like putting the batteries in backwards, basically just flipping it back around and it'll work again. Question on that one there. And obviously, if you chose to flip the sign for the anode, you would turn it into a positive 2.37, then add it to the 0.8. And again, that's perfectly fine to do as well. So cell potential, electrical work, and our Gibbs free energy. The work that can be accomplished when electrons are transferred through a wire really depends on the push behind the electrons. So the potential difference or the voltage is, as we talked about, really a joule over a coulomb of energy. So one sort of joule work that's produced or required between 2 points in a circuit is basically that difference of those electrons traveling from one side to the next. And ultimately, if we do some work, we could use it to obviously run type of motor, like again, sort of batteries, goes out through the thing here and powers your device. The maximum amount of work that we could do is really equal to our Gibbs free energy. And again, that's sort of what free energy is, that as we talked about, sort of the ability to do some type of work. So there is a relationship between delta G and the cell potential. So let's talk about those relationships there. I'll just kind of scroll all these guys through real quick. There we go. So the first one is this one here. Our delta G is equal to minus NF E of the cell. So our delta G is our Gibbs free energy. So that's the energy that's available to do some work. The N is the number of moles of electrons. That is what N is in this case. Now, that is the total amount of electrons that have been transferred. So, for example, I think we had two half reactions a second ago where they each had 6 electrons in the half reactions. And in that case would be 6, not 12, right? Because it's 6 electrons that are being lost and 6 electrons that are being gained. So it's not like add them together. It is really your balanced number of electrons that you have total there. So again, in that example, it would have been 6. F is Faraday's constant, which is this guy right here, 96,500, or, you know, approximately 96,484, if you want the real number, is Faraday's constant. And it has 2 different units there, which are kind of the same units. It is joules per volt per mole. And as we talked about before, a joule over a volt is a coulomb. So that is where the C comes from. A coulomb is equal to a joule divided by a volt. So that's sort of a reduced down version of it. So this is why, you know, when you have a positive cell voltage, it is a spontaneous process, because if we look at this equation and my E is positive, F is a positive number, the number of moles should be a positive number, which means when I have a positive E and that negative there, it's going to turn my delta G into a negative number, and a negative delta G is a spontaneous process. Just like if I had a negative cell voltage, if this guy was negative, that negative at the end is going to turn my delta G into a positive number, which means that the reaction would be non-spontaneous. So that's why when we say positive voltage is good, it remains a sort of spontaneous process should occur. If you have negative voltage, then it is going to be sort of a non-spontaneous process that's going to occur. We could also kind of tie delta E of the cell into our other favorite thing, which is the equilibrium constant. And here's this equation right here. E of the cell, which obviously in both of the equations there is cathode minus anode, just like we did calculating before, is how you get the E of the cell in each of those cases. So once again, E of the cell, still our cathode minus our anode. The E of the cell is equal to RT over NF. R is our gas constant, and it is the 8.314, the guy that has sort of the energy value. Temperature does need to be in Kelvin. N, once again, is our number of moles of electrons that are being transferred, and F is our Faraday's constant. And obviously, RK here is our equilibrium constant. So same sort of relationship. Obviously, if you have a positive E, that means the reaction should be spontaneous. That also means if it is spontaneous, as it is written, it should start making some products, which means we should probably have a large value of K, right? And if we have a negative value of E, would mean our reaction would be non-spontaneous, which means it's not going to the products, right? It's hanging out at the reactant side. And that means that we should have a smaller value of K. So again, all those things obviously should tie together. Personally, I roll with one in the box and just put the numbers in. But if you happen to be at 25 degrees Celsius, a lot of these guys become almost like constants. And you'll sometimes see people use sort of a shortcut version at 25 degrees Celsius, which is 0.0257 volts over N is the natural log of K. Or if you're a more purist than like the base 10 log there, you could do the 0.0592 volts over N log of K. Personally, like I said, I roll with the one in the box and just throw the numbers in even at 25 degrees, and it's just easier to pop them in there. I will say, depending on which equation you use, you might get a slightly different value, especially if you are solving for K, where you might have to do like inverse of the natural log or inverse of log, you know, depending on how you round, you might get a slightly different number. If it's an exponent type number, the exponent should be good, but the front number might be a little bit different depending on rounding. So again, you know, you could just kind of focus on those two. This is our trifecta of thermodynamic stuff here. Basically, if you have delta G, you could use this equation obviously to get to E, or backwards if you have E. If you have E of the cell, you could get to K, and obviously you have K, you get T or G from ones that we've seen in the last couple of chapters there. So, you know, that's sort of how they are all related to each other. This equation that we see here, we'll see in just a bit. It's really derived from an equation known as the Nernst equation, which we'll talk about here in just a second. Yeah. I'm going to say the constants you would be given. Yeah, it should be given Faraday's constant and R and all that kind of stuff. Yeah. So like normal, you kind of need to know the formulas and stuff. Yeah. Other questions? All right. So as I mentioned before, when we look at these equations, again, the stuff that we just talked about is still in play. We got a positive E. That should be sort of a spontaneous process, and we should make some products, obviously. And if we have a negative E, that's going to be a non-spontaneous process. Again, both would result in either more products in a spontaneous positive E, and thus a larger K value, and obviously a smaller K value if you have a negative E. If you got a cell voltage of 0, you're pretty much not much going on there. They're both equally favored. You're sort of at equilibrium at that point. And like I mentioned before, a nice thing about a galvanic cell is, frankly, if you hook up your electrodes and you do get negative, you just unhook them and rehook them the other way, and it should turn it to positive. And that's because you would just make your anode your cathode, and your cathode your anode, and that would throw your negative guy into your positive. All right, so why don't we try one? Calculate the delta G for this reaction, and is it spontaneous here? So in this case, obviously we're calculating delta G. We got some SRP value, so that means E is involved. So our delta G there would be minus NF or E of our cell. In this case, obviously we would want to figure out N, and in this case we could see that 2 looks like a winner there, since it's the same in each case. Our cathode in this case is which one's the cathode? It is the copper, and it is the copper because when we look at the equation, it is +2 to 0, and it is being reduced. And this guy's going from 0 to +2, which being oxidized in this case, and that would be our anode. So to calculate our E of the cell, we would have our cathode, and I'm not going to change the sign, minus our anode, which is negative 0.44 volts. Again, if you change the sign on the bottom guy, you should be adding at this point 0.34 minus our negative 0.44. Gets us a 0.78 volts, and I think that's all we need there. So our delta G would equal minus 2 times 96,500, I think is what we're using there, joules volts per mole. That's a mole, I guess. And our E, which is 0.78 volts. That gets us 0.78 times 96.5 and a 2. Gets us, we'll go down here, minus 1,50540. By the way, these would be in joules. If we divide it by 1,000, gets us about, I'll call it a minus 151 kilojoules, give or take. Any question on that one there? Is this reaction spontaneous? This reaction is definitely spontaneous. It has a positive E of the cell and a negative G, right? So those are two things that screen spontaneity. By the way, you could have figured out spontaneity by just stopping at the cell there, right? It was a positive E, and that would tell you it was spontaneous reaction, but obviously they wanted what the value of G was in this case. Yes. It is. So typically, as we talked about, H and G are typically in kilojoules, and it's really just S is typically in joules. You know, like we talked also about before, you know, if it doesn't really specify, technically you can give it in any unit you want, but very commonly H and G is kilojoules and the S is joules. Other questions? All right, let's try this one. Will 1 molar nitric acid dissolve gold metal to form 1 molar gold 3? Okay, let's take a look and see. So obviously there's a couple of ways we could figure it out, but we could probably just roll with our E of our cell, maybe it might be helpful. So we want our cathode minus our anode. The cathode in this case is, which one? It is not in this case. Because in the question it asks, will nitric acid, which would be a reactant, dissolve gold metal, which would be gold with no charge, to form gold with a +3 charge. That means in this way the reaction is set up, my gold is going from 0 to +3, which means what is happening with the gold? It is actually being oxidized in this case, which means it is actually our anode. And by default, that is nitric acid right there, which is on the reactant side. And this guy would be our cathode. So again, really important to remember, if they give you any information about how it's happening or the reaction, you do need to look at it and not just go by whichever one is more positive. So that means in this particular case, my E of my cell, which would be my cathode here, and my anode. Turn that frown upside down. There we go. And we now would be taking 0.96. And again, I'm not going to change the sign, minus 1.5 volts. And in this case, that would yield us minus 0.54 volts, which technically speaking, do I need to go any further to answer this question? This will actually be a non-spontaneous process, because if we put that into our delta G is equal to minus NFE, with this being negative and this being negative, that's going to give us a positive value for delta G, which is not good. So again, really important to make sure you read it. This is why when you take your gold to the pawn shop, they used to put nitric acid on it. If it's still there, then it's gold. If it goes away, not so much gold, right? You learn these things by watching TV, like the Pawn Stars and stuff like that. You know, they used to do those good things. Any questions on that? Yes. Yep. Yeah, so in the absence of the actual question, right, and you just said, hey, you put these two guys together as in a galvanic cell, you would be correct. The gold would be your cathode, and the other guy would be your anode, and it would actually work in this case. But because the question specifically asks if you took nitric acid and reacted it with gold metal to form gold with a +3 charge, that means if you're going to form it, the gold with the +3 charge has to be on the product side, which means you got to send this guy this way, which means you have to reverse that reaction, which then makes it actually the anode in this case. So that's why it's important, if you are given information about how the reaction is happening, or you're actually just given the overall equation like we were a second ago, I think in the previous problem, you do have to take a moment and look at it to see what is being oxidized and what is being reduced, because it may be a non-spontaneous process in the problem, right? It may not actually work, and you have to actually look at it. But in the absence, like the first several examples we did, where it basically just said, hey, you're kind of making a cell out of these two things, and there's nothing else sort of given to you of how it's reacting, then you could go by whichever one's more positive would be your cathode. And obviously the other one would be your anode in that case. But definitely if they give you any information about how it's happening, you need to look and see who's being oxidized and who's being reduced and follow that. Other questions? Okay. So let's try another one here. You got your, what is the equilibrium constant for the following reaction? And by the way, which one would be our anode and cathode based on this equation? The anode would be which one? It would be the silver. So here we are given the equation, so we want to look at it. The silver starting at 0, ending at +1, again, going in that direction on the number line there, becoming oxidized, which means he is our anode. And the iron is going from +2 to 0, which means it's actually going to the left on our number line there. And it is being reduced, which means it would be our cathode. So again, because we are given the overall reaction, we need to really look at it to see what is happening in this case. And obviously in this case, that is what we got going on there. So I think you have the values given to you there. So you want to look at each of those and calculate the equilibrium constant and see what you come up with. So obviously, so far, we've really only seen one that involves obviously E of the cell and sort of our equilibrium, and that was our E of our cell is equal to our RT-NF natural log of K. So obviously we can see from our balance equation here that N is going to again equal 2, not 4, so you don't want to add those together. By the way, when we do our E of our cell here, this is one more time where we do not want to go by the values, right? We do want to go by what we were just talking about before you started the problem, looking at the equation, because again, it does not agree with that, right? In this case, our silver is actually our anode and our iron is our cathode. So again, really important to make sure you do look at the equation if you are given it. So we pretty much got everything on this side. So let's calculate E of the cell first off, and that would be our cathode minus our anode. And as we earlier determined, it is the iron that is our cathode. So that's going to be 0.44 negative minus, and again, I'm not going to change the sign, so I'm just going to roll with the negative there and subtract it. And that will get us here a 0.44. Say 0.8, I think a negative 1.24 volts if I didn't mess that up there. Now we have E of the cell. We can take our minus 1.24 volts equals our 8.314. Our temperature, which is 25, is a 298 Kelvin, natural log of K. And our N is 2 moles, and our Faraday's constant, obviously 96,500 joules volts per mole. I'm going to clean up all the numbers on the right-hand side there before the natural log. So we've got 8.314 times 298 divided by 2 and divided by 96,500. That gets me minus 1.24 volts equals 0.012837 natural log of K. We're clearly going to bring that to the other side there. And that's going to be 1.24 divided by my answer. That is going to give me a negative, I believe, here, 96.595. I'll round a little bit there. Equals our natural log of K. To get rid of the natural log, we need to take the E of both sides, right? A little E of that guy and an E of this guy. That is going to give us a K value. I should probably make my negative there. That would be good. And do that. We'll call it 1.1 times 10 to the minus 42. There. Any questions on that calculation there? Now, if you use one, again, the kind of rounded versions of those equations, it might have a slightly different number. And also, if you round it a little bit different, especially when you took the E at that point, you may get a slightly different number. But your exponent number, I think, should be in the ballpark there, you know, as long as you didn't do a super amount of rounding. Does all this stuff sort of agree? Our E of our cell is positive or negative? It is negative, which means this reaction is spontaneous or non-spontaneous. I think that's both answers, but I think the right answer is non-spontaneous, right? Because it's a negative E, right? It should give us a positive G, which would be non-spontaneous. And because it's non-spontaneous, that means we should have mainly reactants. And that means that our K value should be small, which obviously that is small. Yeah. So again, Those are things you want to think about to make sure all those things sort of are in agreement, that you didn't maybe do any weird math or anything like that. Any questions on that there? Yes, sir. Yeah. Yeah, so all non-spontaneous, well, you can make a non-spontaneous reaction occur by applying an external sort of source of energy. That's sort of what electrolysis is making sort of non-spontaneous processes sort of occur. We'll talk about electrolysis towards the end of this chapter, but yeah, you can do that. Alternatively, you can basically flip everybody around here, I'm trying to say, so, kind of make your silver your cathode. If you're building like a galvanic cell or something like that in this situation, your silver your cathode, and obviously your iron your anode, and that would turn your E into a positive number, right? And then it would become a spontaneous reaction at that point. But specifically here, we're talking about obviously a reaction of the iron 2 going that way, and that's why. So yeah, there's a couple different ways you can kind of do it. In a galvanic cell, pretty simply, you could just kind of, if you have a sort of a cell build, just flip around the electrodes, the clips to it, and it would work. And obviously you can apply external sort of energy to make a non-spontaneous process work. One last thing we're talking about before we wrap it up here for the week is the effect of concentration on the cell. Yes, I said that, so the end is near, in a good way, I suppose. So much like what we saw when we talked about delta G here, we did have this equation, as we sort of talked about. You can kind of think of it as, obviously we used this when maybe we didn't have something that was in a non-standard sort of state. So for example, I think you guys had on that lab a question where you had a pressure of 10 atmospheres, and that obviously is a non-standard condition, right? So 1 atmosphere would be a standard condition, so you would need to use this equation to calculate the effect on delta G. So since that delta G is related to obviously RE of the cell, putting them together gives us what is known as the Nernst equation, which is this guy right here in the center. These guys on the bottom are much like what we saw in that previous equation, just kind of reduced down at 25 degrees Celsius. But if you use the one in the middle, you could just put in the numbers. But this is, again, sort of the same situation. This is sort of E of the cell, if you want to think about it under a non-standard sort of condition. This is obviously the cathode minus anode, like we've been doing, that you would find obviously from the table. And then pretty much everybody else there is everything that we've been using, the same R value, F, and T in Kelvin. And then, of course, because we're in this sort of non-standard condition, instead of K, right, we are going to use Q, which is our products, right, over our reactants. Also, again, making sure we use our exponents, right, for our coefficients as our exponents when we do this. So in this case, to also maybe answer a question that you were just asking, you could use this, for example, if you had a non-spontaneous reaction, and maybe by just playing with the concentrations, or if you had gases or pressures, you could, in theory, turn sort of a non-spontaneous reaction into a spontaneous reaction by changing concentrations or pressures or even temperature. That can perhaps turn, again, under normal standard conditions, a reaction being non-spontaneous into a spontaneous reaction. So that's another way that you could kind of play with certain things and perhaps turn something that would be non-spontaneous under normal conditions into perhaps a spontaneous reaction. And again, these are just sort of the reduced down versions of that equation. You could plug everything into there. This equation really is where we saw the previous equation comes from, because when we get to at equilibrium, obviously E is going to equal 0 and Q will equal K. And if we do that, that gives us 0 is equal to E naught minus RT NF natural log of K. And rearranging that is basically where we got the equation we just used on the previous problem actually from, is sort of from this equation. At equilibrium is essentially where that equation is derived from. This one, though, unlike this one up here, this actually is a subtract. Yeah, so this one is a subtract when you're doing E of the cell, not an adding of it at that point. So again, we would use this equation, very much like we use the delta G equation up on top, if again something is not under standard conditions. So maybe you're giving pressures that aren't 1 atmosphere, or concentrations obviously that are not 1 molar. So let us finish out the week here by trying one here. Yes. And let's calculate, will this reaction occur if the concentration of iron is 0.6 and the concentration of cadmium is 0.1? And again, if you look at the overall equation, we see the iron going from +2 to 0, which means it is gaining electrons and being reduced. So once again, looking at the equation tells us this should be our cathode, and this guy should be our anode as it goes from 0 to +2 in this particular case. And once again, that may not agree with obviously what you see in the SRP table value there. So we want to make sure we do look at the equation always if you are given one. Let's take a look. So a couple of things on this one. Clearly, we do see some concentrations given to us, and they are not all 1 molar, which tells us, again, sort of a non-standard condition. Once again, if we went to the SRP table, you might be inclined to say that the cadmium should be your cathode based on the value that you see there. But once again, you do want to refer to the equation since it was given to you. And we actually see the opposite here, that is actually the iron that is our cathode. So we will use our Nernst equation because we're definitely under some non-standard type conditions happening here. That's an RTNF, natural log of Q. And in this case, we pretty much can calculate everything on the right-hand side. We do want to calculate our E of our cell. So the E of the cell here, once again, would be our cathode minus our anode. And by looking at the equation, and we're going to take our iron, which looks like it is minus 0.44 volts, minus, and again, I'm not going to change the sign because I'm subtracting here. And that is going to get us a minus 0.44 minus a minus 0.4, negative 0.04 volts. So that would be the E of the cell under standard conditions. So under standard conditions, is this reaction spontaneous? It is not, right? We got a negative voltage there. So it's a non-spontaneous process under standard conditions. So here we're not under standard conditions. We sort of played with the concentration. So let's see if that did anything to help. And we can kind of put our numbers in here. Our N is going to be 2 in this case. And we also want to calculate Q. So Q would be our products, which should be the cadmium in this case, divided by our iron. We're not worried about the iron with no charge or the cadmium with no charge because they are solids, right? So they should not be included in here. And that's why you're only given 2 numbers. And that would be 0.01 divided by 0.6 in this case. And that gets you 0.01 divided by 0.6. We'll go 0.016667. All right, so I think we got all of our numbers now. So we got E is going to equal minus 0.04 volts minus our 8.314 joules Kelvin mole and our 298 on that divided by our 2 moles and our 96,500 joules per volt per mole. And that's going to be the natural log of our number on the bottom there, 0.016, that number right there. All right, if we clean up everything on the right-hand side, we will take the natural log of that number, 0.01667. We're then going to multiply it by 298 and multiply it by 8.314, hit equals. We're going to divide it by 2, hit equals, divided by 96,500, hit equals. That is going to clean up everything on the right-hand side there to this guy stays the same. minus a minus 0.052, we'll call it 6 volts. Now finally minus 0.04 minus our number there, 0.0526, gets us approximately a cell voltage of 0.013 volts. Is this reaction spontaneous? It is barely. You got a little bit of voltage, not a lot to call home about, but you did get some positive voltage here. So this would be spontaneous. So again, what this demonstrates is obviously under standard conditions, if you ran this this reaction with everybody at 1 molar, it would be a non-spontaneous process. Here, by just kind of playing a little bit with the concentrations, again, not a lot of voltage achieved here, but you were able to get some positive voltage, which then would mean it would be spontaneous. So by using the Nernst equation and non-standard conditions, you can do things like this, sort of figure out if you play with concentrations or pressures or temperatures, there could be a way to turn a non-spontaneous process under normal conditions into a spontaneous process by playing with those sort of factors. Any questions on the Nernst equation? Yes. That is everything that's on the right-hand side here. So all that, I took the natural log of 0.01666 and then times it by 8.314 and times it by 298 and then divided it by 2 and divided it by 96.5. So basically everything to the right-hand side of the minus side will get you that number. Yep. Other questions? All right. I think that's plenty of torture for today.